Good evening, everyone. How are you today? I'm excited to welcome you back on this platform where we look together at CHM416 Organic Synthesis. My name still remains the same, Professor Olayinka Ajani. Today we shall be looking at the topic 7 for week 7, which precedes the last facilitation for this course. So you are welcome on board for today. And I enjoy you to be set at alert because we are going to be having a lot of exciting moments together. Thank you and stay blessed. Today we are going to the unit 2 of module 3 with specific title, Vitic synthesis of carbon-carbon double bond. And that's this with using the Vitic reagent as a very valuable synthetic tool for olefination. That means getting the synthesis of alkene by using this valuable reagent called Vitic reagent. And it's more useful and very reactive at its halide form, where the positive charge is on the phosphorus and the negative charge is on the carbon that is linked to the phosphorus. Vitic synthesis is just an exchange between a carbonyl and a Vitic reagent to form an alkene. Oxygen of the carbonyl will come to the position of the carbon, taking the position of that carbon to form phosphorus oxygen bond, while the carbon leaves that position to join on the double bond to form alkene. At the end of this topic 7, the learner should be able to, number 1, explain methods of preparation of phosphorus halides, which are the Vitic reagents. They should be able to discuss the mechanisms and the stereochemistry of Vitic reaction. They should be able to describe the special form of Vitic reagent or reaction that is called Turner-Wordsworth-Hemmond reaction. It's a collaboration between three different scientists, and is the one that is able to provide solution to where there are limitations in ordinary Vitic reaction. So it's a modified version of Vitic reagent to take care of the limitations. The student should also be able to give some synthetic application of Vitic reaction. And then lastly, it should be able to list some advantage of this Vitic reaction. Introduction. Vitic synthesis of carbon-carbon double bond is very important and crucial as one of the main synthetic tools to achieve alkene. And it's so easy and so cheap because immediately the Vitic reagent is reacting with a carbonyl compound of either aldehyde or ketone. The oxygen on that carbonyl will just go away to link and bond with the phosphorus of the Vitic reagent, while the carbon that is directly linked to the phosphorus of Vitic reagent will go and occupy the place of the oxygen to form an alkene. It allows one to selectively prepare alkene. It allows one to selectively prepare alkene in a manner that is unmatched by any other method. The starting material are usually alkyl halide and an aldehyde or ketone. It's a reaction between a carbonyl compound, which is that of aldehyde or ketone, with a reagent species known as the phosphonium halide. When we're talking about phosphonium halide, which is the Vitic reagent, it's the one that reacts with aldehyde or ketone to cause olefination reaction. And halide is a species with a positive and negative charge on adjacent atom. So when we are talking about Vitic, there are some things that are peculiar that we need to look at. We'll be looking at that in detail very soon. The action was first described in 1953 by Vitic and Geisler, and is probably the most widely recognized method for carbonyl olefination. That means carbonyl compound, turning them to alkene. Wittig is one of the best methods to do that. Wittig reaction has advantage of total positional selectivity. That is, an alkene always directly replaces a carbonyl. Maybe we can just quickly look at this before we go into the detail. When we are talking about an halide, phosphonium halide, phosphorus has expanded objects. The phosphorus is linked with 3-phenyl group, like a phosphine. It's a phosphine group. If such phosphorus is linked to a carbon, for example, the phosphorus will carry the positive charge, the carbon will carry the negative charge. So these two adjacent atoms to each other, which is the phosphorus and the carbon, have positive and negative charge that hold them together in that attraction. This is what is called halide. That's why we're saying, when we are talking about that, the first thing we talked about was talking about the halide formation from the reaction. And then afterward, that halide can now be, let's say, for example, we have a carbonyl compound. If you have a carbonyl of either aldehyde or ketone, then the halide of phosphonium can react with it. And what we are just trying to say is that in such a reaction, the simple thing that happens is that the CH2 here goes away to replace this oxygen. And by doing so, this carbonyl has already become an alkene. Olefination of carbonyl has happened. Then the oxygen that left that position will come back and replace where the methylene group left. And that will make us to have a product that is now neutral in its nature. So this is the reaction product. The CH2 will leave the phosphorus side to replace the oxygen of carbonyl to form alkene. The oxygen of carbonyl will leave to come and form phosphoxide with this. So this is the neutral form of the final product. If you want the charged particle form of the final product, then it is for this one and this one. But the final product is always preferred to be a neutral molecule to avoid further reaction. So it's always better to have the final product in this form. But the starting material wants to be in charge form. Starting material, we have CH2 negative, and then we have H plus, P plus. So that will easily initiate a reaction and proceed further. The factor that influence E and Z stereoselectivity are well understood and can be readily controlled by phosphorus reagents and the reaction condition. What we are saying is that in that situation, you are able to know clearly how cis and trans isomers are formed. Therefore, you are able to control that by making some synthetic adjustments to whatsoever your precursors are. So a wide variety of phosphorus reagents are known to participate in Wittig reactions. So these are divided into three. The first one is normal classical Wittig reaction of phosphonium halide. The second one is Ormer-Wadsworth-Emmons reaction that made use of phosphonic ester anion. And the last one is Orner-Wittig reaction of phosphine oxide anion. So each of these specific type of Wittig are dependent on the precursor or the starting material that initiates the reaction. When you are using phosphonium halide, you are dealing with classical Wittig reaction. When you are using phosphonic ester anion, you are dealing with Ormer-Wentworth-Emon reaction. And when you are using phosphine oxide anion, then that is on a Wittig reaction. Each of these reaction types has its own distinct advantage and limitation, which you must know. And this must be taken into account when selecting the appropriate method for a desired synthesis. If you know the limitation of the classic Wittig reaction, if the synthesis you want to do at that time will prone you to such limitation, then you know that you are not to pick classic Wittig reaction method. That's why you must know each one of them and their advantages and limitations. And when you know that, you know when to use any one of them. Preparation of the ylides. That is the Wittig reagents that will be used in Wittig reaction. Ylides are prepared from alkyl halide in two-stage mechanism. The first one is the nucleophilic attack of the alkyl halide by the phosphine. And the second one will be the phosphonium salt form is treated with N-butyl lithium in either dry ether or anhydrous tetrahydrofuran to form our phosphorus halide, which is called the Wittig reagents. So you remember we said phosphine is starting to work, and phosphine, you said the phosphorus is bonded with 3 phenyl group. That is phosphine. 1 pH, 1 pH, 1 pH. So you see that your phosphorus is bonded with 3 phenyl group. How do you prepare your Wittig reagent? You will react this phosphine with alkyl halide of choice. If you want to add, for example, 3 carbon atom to a ketone to form another longer alkene, alkyl halide you have to use must have 3 carbon. Because at the end of the day, is that 3 carbon that is from the alkyl halide that will break away from the phosphorus later to go and replace the position of the oxygen to form the alkene. So the nature of the alkene products you want to get, you get it right from the reaction in the beginning. If you want to add 5 carbon to your C-double bond to get an alkene that is 5 carbon higher than the normal ketone that you started with, then you know the alkyl halide you want to use must have 5 carbon in a sense. So let's look at, for example, we want to generate a Wittig reagent that will have 3 carbon in the negative charge, so that it can go and add 3 carbon to the ketone. So if you want to get an alkene from a ketone by having additional 3 carbon straight chain, you start that right from your Wittig reagent. So phosphine is here. We have 3 carbon straight chain, 1, 2, and 3. So we have alkyl here is C3H7, and the halide there is bromine. When you treat that with phosphine, what will happen is that there will be attack. And when that happens, we are going to be forming internal positive charge on phosphorus and external negative charge on the bromine. So when this happens, you discover that this C3H7 get attached to the phosphorus, and by doing so, phosphorus has used something. Remember that phosphorus in trihalide form, in trivalent form, is having a lone pair of electron on him that he has not used. You remember that phosphorus is like it's the nitrogen family. It has 3 bond pair here and 1 lone pair. You use that 1 lone pair to nucleophilically attack the alkyl halide. That's why we say the first method, the first step in that synthesis mechanism is nucleophilic attack of the alkyl halide by the phosphine. Phosphine has a lone pair of electrons, which is rich and has capacity to attack anything. So when that happens, it attacks this carbon, then the bond that is binding carbon and bromine together will break away on the bromine as a negative charge. So having said that, you discover that there will be 3 phenyl group on that phosphorus. These are the 3 phenyl group on that phosphorus. But now that phosphorus has used its lone pair to form bond with carbon, phosphorus has become positively charged. And these are the 3 carbon right now. The CH2, number 1 CH2 here is what you have here that is directly attacked by the phosphorus. And next that attached to him is this middle one. And the last attached to him is this methyl group. So you can see here right now that we have conveniently brought in 3 straight chain carbon to form our halide, which is the Wittig reagent. Now, when you look at this now, you remember, if you don't forget, we are saying that the number of carbon you want to come and replace the oxygen of your carbonite is what will be depending on what you have already given the halide the opportunity to form. So we want 3 more carbon to come on that carbonite to form alkene. That's why we have used a alkyl halide that have 3 carbon. And here you are now having the Wittig reagent that have 3 carbon. But you see here right now that the positive charge is on phosphorus. The negative charge is counterbalancing it by the bromine anion. But remember that Wittig reagent, it is the phosphorus and the adjacent carbon atom to him that are supposed to carry positive and negative charge. So this is a pseudo Wittig reagent because it has not come fully to that term where it's needed to be positive and negative. The negative is still on the halide. So what we do at this stage is to treat it with N-butyl lithium. N-bully. N-butyl lithium, of course, at that stage, we now allow the abstraction of the proton here, acidic proton. Wherefore, the bond between that proton and that adjacent carbon will go on that adjacent carbon as negative. So at that time now, N-bully has allowed you to get a full Wittig reagent or a full halide of phosphorus from this pseudo one. So at the end of the day now, you now discover that, oh, the carbon adjacent to phosphorus is carrying negative, while the phosphorus is carrying positive. So this is the phosphorus halide. This is the phosphorus halide. And it's your Wittig reagent that will start the reaction. So if you have to now, for example, react this one with methanol, an aldehyde that has only 1 carbon. If you try to do that, it's because you have emphasized that you want to get an alkene that have 4 carbons. Because your carbonite has only 1 carbon, and you need 4 carbon in your alkene, so you have intentionally used bromide that have 3 carbon. And you have from there get a halide that has 3 carbon. So what we are saying at the end of the day is that the oxygen here will leave. The oxygen here will leave. So the 3 carbon you have intentionally incorporated into your halide will break to come and replace it. So the first carbon here breaks here. That hydrogen on one side is linked to CH2 on the other side. CH2 on the other side. And that CH2 is linked to a CH3. That will be the first thing that will happen. Then the second thing is that where these breakages occur, the oxygen will come there. So you have your phenyl group, 3 of them, attached to the phosphorus. So where that carbon broke away, then the oxygen is coming there to form this. So this will be the side product after the alkene has been formed. So you have used only one carbon ketone, one carbon aldehyde, which is methanol, to now form 4 carbon alkene, which is but1-ene. So there are two major things that are the step in the halide formation. The first thing is that there is going to be a nucleophilic attack of your alkyl halide of interest by the lone pair on the phosphorus of your phosphine. Then after that, the phosphonium salt that is formed will be treated with N-butyl lithium in dry solvent of ether at very low temperature, around -78, to now form your phosphorus halide, which is the Wittig reagent. It is this halide that you now react with your carbonate compound to now get alkene product form. So to get your halide, there are 2 steps: nucleophilic attack of alkyl halide by phosphorus, followed by the reaction of phosphonium salt with N-bully to form halide. But when halide has been formed, then it can react with carbonyl of aldehyde or ketone to form the final product in another 2 steps, which you are going to be looking at very soon. So if you are talking about starting from the scratch to get your alkene, it requires 4 steps of mechanism: 2 steps for the halide formation and 2 steps for the alkene formation. So we have looked at the 2 steps for the halide formation. So let's look at the step for the alkene formation. After you are treating, when you are treating your halide of phosphorus salts with a ketone, it involves 2 intermediate species. The first thing is that when the halide of phosphorus reacts with your ketone or aldehyde, it first of all forms a diionic compound called beta-hene. Remember that word, beta-hene. Beta-hene. And afterward, that beta-hene, because of the positive and negative charge, have now come to 2 different atoms that could close up on each other. Then it will end up forming a 4-membered heterocycle, where the oxygen and the phosphorus are the major key player in closing up that ring system. And that 4-membered ring is called oxaphosphatane. Oxaphosphatane. These are the 2 steps that will be required before the final readjustment for ketone to be formed can happen. And if you are talking about that, we can just quickly look at that in the picture. Of course, we have known the overall reaction to form alkene, but what are the steps there? You can see your phosphorus here with the 3-phenyl group, but the negative charge is not yet on this carbon. That means the first stage has been formed, but you need to react it with N-bully or something, a lithium species, in order to form, abstract the acidic proton from CH3 to now make it CH2-. When that happens, you now have your halide. This is now your halide because the positive and negative charge are now on the 2 adjacent carbon. Here, the positive is on phosphorus, but the negative is on the halogen of the alkyl halide. So without mincing word, you can know that how this is formed is that your phosphine was reacted with methyl iodide. That's why that is formed. So for the negative to leave the iodide to come on the carbon, you treat it with lithium compound, and that gives us CH2 negative. This one can be in canonical form, of course, to form this. This is the neutral form of it. This is the charged particle form of it. Now, here we now want to react this one with this kind of carbonate. It's a ketone that has phenyl ring on both sides. So if you're doing that, what will happen is that the negative charge on your CH2, always remember, negative charge is electron rich, negative charge is nucleophile, negative charge is the only one that can initiate nucleophilic attack So if you look at that, phosphorus here cannot do it anymore because it has lost its lone pair to become positively charged. It's deficient, it's an electrophile. But CH2 is rich in electron. So it's this CH2 that will attack the sp2 carbon of your carbonyl, thereby leading the pi bond of that to be a negative charge on the next electronegative atom called oxygen. When that happens, you discover that what you will form eventually will be something that have an affiliation for the oxygen and the phosphorus to interact. If you look at that very well, you have your CH2 here. So CH2 has attacked a carbon who now have O negative and 2 phenyl group. The first one is the betahene, which is diionic group. So when this attack this, you see what you have here? We have a positive charge and a negative charge all in the same molecule. And that means that is your betahene. However, if you look at this betahene now, you discover that phosphorus and oxygen has a strong attraction for each other because oxygen is rich with minus charge, phosphorus is deficient with plus charge. And now they have tendency to form a pseudo 4-membered ring because by the time the oxygen here collaborate to form bond with this, it will close up to form a 4-membered ring. And that's why you see the 4-membered ring that you see here is as a result of the negative on oxygen closing up on positive on phosphorus. And that's why this 4-membered ring that is formed is called the oxaphosphatane. Now, it is in this collaboration of this 4-membered ring that an internal rearrangement now occurs. You see, oxygen and phosphorus now have a stronger affiliation for each other because the bond between those two we want to hold intact much more than between oxygen and the other carbon. So when that happens, we discover that the bond here will break up to concretize the bond between the phosphorus and the oxygen. And for the phosphorus not to exceed its valency, the bond between him and the next carbon is breaking away to form a pi bond in that regard. So when you look at that, this interaction has made oxygen that is coming from this place to have released himself from that relationship to concretize his relationship with phosphorus. So you end up having PH3P double bond O, PH3P double bond O. That's the side product. Now, what will you have here right now will now be a double bond here on carbon that have 2 phenyl group. Of course, you remember that that carbon that is up there is CH2. So there, here is hydrogen, here is hydrogen. So you have been able to form an alkene by just removing the oxygen of your ketone and replace it with CH2 coming from halide. You see the CH2 here. And the oxygen that is living here in the return went to go and get himself attached here. So in the overall reaction mechanism from the scratch, olefination with halide or Wittig reagents is 4 steps. The first 2 steps will be for the formation of the phosphonol halide, while the last 2 steps will be for the formation of your alkene. And he said in the last 2 steps of forming alkene, when the negative charge of the carbon of halide attack the carbon of the ketonic group, we said it's going to form a diionic compound, which is called beta-heme. And by the closeness of oxygen to the phosphorus, one, and by the negative on oxygen and positive on phosphorus, strong attraction comes between them to close up and form a real line bond between themselves. And that is what leads to a four-member ring called oxaphosphatane. Is this oxaphosphatane that internally rearranges itself to get to a more stable product and break into two. One will now be our alkene products. So once you understand this, you have understood everything about Wittig reagents. So if you are asking for the mechanism, these are the mechanisms. But if you are not given the, if you are not asked to give the mechanism, they are just asked for the products, it is the cheapest, is the cheapest question you can ever experience in it. Like for example, if I say, let's look at example of a reaction where we have there are 3 phenyl groups on this. 3 phenyl group on this. And here we have a CH2. Or let's say we have a CH that is linked to CH2. That is linked to a 3-membered ring. Here now you have minus, here now you have plus. And they say you should react this one with propanol. And they are asking you what is the product of this reaction. Propanol, remember, is the same thing as acetone, 3-carbon system, which is carbonyl on carbon number 2. If they are asking you what will be the product of this reaction, they are not even asking for mechanism. Things like this are the cheapest. When you look at that, you discover that this is already halide of your phosphorus, which is the Wittig reagent, because the phosphorus and the carbon adjacent to him carries the charge. So this becomes easier. This is the place of breakage. The oxygen here will be removed, then this CH will come into that place. So if we have that, we say C double bond, we have CH3, we have CH3, so you just come here and cut CH, CH, and the other side of it will now be CH2 linked to a 3-membered ring. Now, if you look at this very well, this is not like the other one that we have CH2 coming in. If the CH2 is coming in, to this side will be hydrogen, to this side will be hydrogen, so there is no disparity. But immediately something that is not hydrogen on both sides comes in, Wittig reagents tend to give a mixture of alkane. If you look at this very well now, around this double bond of stereochemistry of this double bond, the bulky group on this carbon up is this side. Hydrogen is not. The bulky group on this carbon of the double bond down is both of them. So immediately you are having the bulky group on the same part, then you are having the Z isomer. But if it's on the opposite side, you are having the cis isomer. But here you don't need to have that. Why? Because CH3 and CH3 are equal. So whether this one is to the same side or to the opposite side, you cannot determine. But if this one has been a CH2, CH3, then it will have been easier to say, oh, this skin can be, okay, this one will be the more bulkier than CH3. This one is more bulkier than hydrogen, and they are on the other side of the plane. Because they are not the same thing, instead of calling them trans isomer, you call them E isomer. However, If the bulky group are on the same side, let's say, for example, you have your CH3 to this side. Let's say you have your CH3 to this side, and you have your CH2, CH3 to this side. You still have to consider the two carbon that carry the double bond. They are the determining factor. The carbon that carry the double bond up here has a lighter one hydrogen and has a bulkier one methyl cyclopropic. This is the bulkier one for that group. The second carbon of the double bond here has a lighter one here as methyl and has a bulkier one here as ethyl. When you look at this here now, the bulkier one is here, the bulkier one on the hub is here. So they are on both sides of the plane. But because these two bulkier ones are not the same, if they are equal thing, we should have called them cis isomer of alkene. But because they are not the same thing, instead of calling it cis, you will now call it Z isomer. So a additional modification of cis isomer is what lead to Z isomer. Additional modification of the trans isomer is what leads to the E isomer. So when we have Z and E, it means the two bulky group that allow you to know whether they are on the same side of the plane or on different side of the plane are not the same thing. That's when you have E and Z. You see the bulkier group here is ethyl group. The bulkier group here is methylene cyclopropic group. They are not the same thing. Therefore, this will lead us to call it Z isomer instead of cis isomer. Okay, so this is the end product of this. If you break it here, you know what has happened. This has been removed and CH2 has replaced it. CH2 has been removed from phosphorus and oxygen has replaced it. But the overall thing is in 4 steps. Mechanism of Wittig reagent reaction. There has been much debate as to which of these two species play the most important mechanistic role and their influence on the reaction in the overall. It was generally accepted that beta-heme is more important intermediate. However, recent research report using phosphorus labeling NMR study discovered something completely otherwise. It has been known generally before that beta-heme is the more important intermediate in the mechanism, but recently the phosphorus 31 NMR, that means labeling isotope, was used to know that, oh, when you put phosphorus 31, then you are able to monitor the progress of that phosphorus to the end of reaction, because it's not just ordinary phosphorus. Now, just like when you are talking about carbon, carbon is 12. When immediately you are using carbon 13, you are using another isotope of carbon that's different from ordinary carbon. So with that labeling on it, you are able to monitor its progress from the beginning of the reaction to the end, to know when it changed, to know when it transformed. So you are able to know that how did the mechanism go. So when this phosphorus 31 NMR study was actually used to investigate, they discovered that what has been generally accepted to be the fact that beta-heme is the most important intermediate was not the case that they found out. This supposition is further supported by a recent calculation that revealed that oxaliphosphatane are of lower energy than the corresponding beta-heme. So we are saying that looking at the mechanism of this reaction, we want to know the mechanistic detail. Is it actually the beta-heme that is the most important intermediate? Or is it the oxaliphosphatane that is 4-membered ring that is the most important intermediate? So they have generally believed that it's the beta-heme before, but the proton label isotope NMR proved that no, oxaliphosphatane is the most important intermediate. And having said that, calculation also has established that oxaliphosphatane are of lower energy. And you know, the lower the energy, the better the stability of the compound. And this, from these two strong point. So we have been able to establish that out of the two intermediates, actually, in the recently, oxaliphosphate is more important. Most accepted mechanism. In view of the aforementioned, the currently accepted mechanism for phytic reaction is as shown in the scheme. You see the carbonyl here reacting with the phosphine. And when it's reacting with phosphine, there are two things that have happened. One, it's possible that the oxygen closes up on the phosphorus to form a cis oxaliphosphatane, or it closes up to form a trans oxaliphosphatane. That's why we are saying when that R and R prime are not the same thing, then you will have mixture of products, the cis and the trans. So by doing so, he said that, oh, there are two that will be formed. This R and R prime are on the same side of the plane. That's why they have the dash bond. And here we have one dash and wedge bond in that of the trans, so that they are not on the same side of the plane. So that one up, that oxaliphosphatane up, is a cis oxaliphosphatane, which will arrange itself to form a Z alkane. Why is it not cis alkane? We call it Z alkane because the two bulky group are not the same, R prime and R prime prime. Even though they are on the same side of the plane, instead of calling them cis, they will now call them Z. So the one down here is a trans isomer of oxaliphosphatane, which when it's released, because the R prime and R prime prime are not the same thing, the bulkier group are not the same. So instead of calling it, they are on the same other side of the plane. Instead of calling them trans, they will call them E isomer. Stereochemistry of Wittig reaction. Phosphine is a major steric factor governing stereochemistry of the addition. If you remember your phosphine, a phosphorus have 3 benzene rings, are as big as they are, they will create bulkiness around that phosphorus, and therefore there will be steric hindrance there. So you can see example of what we are saying in the structure below. You can see this phosphine have 3 benzene rings. So steric effect is already being created at this side. And when you have this now, as our Wittig, you break it here. The oxygen of your ketone will come and join with this phosphorus as a side product. Then this carbon will come and link to where this oxygen left. And when it's linking to that place, it can link to it towards the right, or it can link to it towards the left. And that's why we are saying, if it's linked to it towards the right, you can see the double bond here. The bulky group here is to the right. The bulky group to the lower carbon is to the right. So the bulky group are on the same side of the plane. So we have the Z isomer. We have the Z isomer. But if it is to the other side, here you see the bulky one here is to the right, to the left, but the bulky here is to the right. So this is like a trans isomer. So we call it E isomer. So phosphine is a major steric factor governing stereochemistry of addition. Simple compound. Reaction is Z selective and kinetic control. Minimize anything that will equilibrate the beta-heme. If need to form E isomer is there, which is thermodynamically controlled. The E isomer is more stable under heat because it's a transform, so we can withstand high heat. It's thermodynamically favored product. But the Z is kinetically favored product. At a high temperature, the Z cannot survive. So it is possible that Wittig reagent can give you the mixture of these two. It is also possible that you can want to intentionally control that what I need at this time is the Z isomer. I don't need the E isomer. Or what I need to do is the E isomer. I don't need the Z isomer. This is the beauty of Wittig reagent. You're able to control it to your taste by selectively adjusting your precursor to get you to where you are going. So we have said that if need to form E isomer, which is thermodynamically controlled, is there, then one should intentionally isomerize the beta-heme to lead to E isomer as the most stable product. Schlosser described this to involve adding a mole of strong base like phenyllithium to the beta-heme. So if at the stage of beta-heme, you don't want to form mixture of E and Z isomer, and the Z isomer that is easier to form at a lower temperature because of the kinetics, you don't also want to form that, then you can intentionally form the E isomer by just adding a little 1 mole of strong phenyllithium to the beta-heme intermediate. Without carefully controlled mechanism, Wittig reaction with aldehyde and ketone will end up forming both the mixture of C and E isomer. So you know you can form the mixture of the two. So you can also know how to allow it to form one and not the two. That's why Wittig is very good. If you add 1 mole of phenyllithium to it at the beta-heme intermediate stage, it will end up to give you E isomer alone. Unna-Wadsworth-Hemmond reaction. The Unna-Wadsworth-Hemmond reaction is a chemical reaction used in organic chemistry of stabilizing phosphonate carbanion with aldehyde or ketone to produce predominantly E-alkene. Can you see? So if you want to produce E-alkene, your aim is not to get a mixture of E and Z. Then on our Wadsworth-Hemmond reaction, AWE reaction will help you to achieve that. One limitation of Wittig reagent or reaction is that the phosphonium halide that contain the stabilizing group next to the negatively charged carbon are not reactive enough because of that bulky group of phenyl group, 3 of them. They are not reactive enough to undergo desired reaction with a carbonide. The stabilizing group can spread out the negative charge via resonance and thus reduce the nucleophilicity of the carbon. So this problem is solved actually by using the more reactive phosphorus compound. And that's what we are saying, that if you are using phosphine, because of the steric hindrance and the unreactive nature, it cannot proceed to give you E. So if you want to get E, you can get a phosphorus compound that is much more reactive than the phosphine. And that's what leads us to getting that phosphonate ester group. So if you are using compound that's tri-ethyl phosphate ester, then you remember that you know that that phosphorus is more reactive and then allow you to proceed to get your E isomer. This is an example of what we are saying. You look at this phosphorus now. Not correct that in your course material. This is C2H5O. This is C2H5O. This should be oxygen. So this is C2H5O. So you can see there are C2H5O, 3 of them. So instead of the 3 phenyl group that has created steric hindrance, you can use 3 ethoxide group. And that leads to the formation of, when you react it with this benzic bromide, it leads to the formation of the ester. And when the ester is reacted with sodium hydride in the presence of the ketone that you want to react with, it makes it to form the ester salt and therefore allow the reaction to proceed through that realm to get the E isomer. The bulky group around this double bond is on the right. The bulky group around this double bond is on the left. So this will end up forming E isomer because you have now changed the phosphine to a more reactive phosphorus compound called phosphonate ester carbanion. There's another advanced nature that was brought on this HWE reaction. Remember, we call the HWE reaction on a Watford-Hemon reaction. HWE. There is a processor called steel who added another thing to it, and that makes us to have another procedure called steel HWE reaction. And what led to that additional thing from steel is that a question we can ask ourselves, what if you want to have a Z isomer? We have seen now that HWE has provided our phosphorus compound to be much more reactive by using the ester of it, and therefore predominantly He isomer of alkane was formed. But what if we want to form Z isomer? Is all hope lost? Then still was able to do something that can make us to strictly get the Z isomer. We say you will need what we call the steel HW procedure. It involved the addition of trifluoromethyl group. You remember that fluorine has the highest electronegativity in periodic table. So if 3 fluorine are added to 1 carbon, there is a cumulative electron power on that. So when you use the ester that have trifluorophenyl group, you use ester that have trifluorophenyl group, then you discover, oh, the reactivity has been completely enhanced, much more than what it is. So when that will proceed by that inversion of configuration to produce the said isomer. HWE procedure will help us to produce strictly the He isomer. However, if we allow the ester phosphate group to carry trifluoromethyl group, then that strong concentration from and strong reactive nature from the phosphorus makes it to proceed to the Z isomer. Synthetic applications of VTIC. These are some of the examples of the synthetic application of VTIC reaction. We can see the product that is formed. Because the carbonite is expected to close up on the alkyl group. But when one compound has carbonite, that are 2 of them, and the alkyl group has 2, then they can close up to form a new membered ring. These are some of the products that are very crucial and very important. You can see the alkyl halide here. There are 2 alkyl groups. And when you look at the carbonite, there are 2 C-double bond groups. So by that, you will form the VTIC reagent that have 2 faces to disconnect. Therefore, 2 oxygen from the carbonite will come there. So that will end up having this place linked with a C-double bond of this carbon. 2, 3, number 4. 2, 3, number 4. So this one is now by just making sure that you have di or 2 phases of reaction linkage, then you are able to get something better. So the same thing with all the products. There, you try as many as you want. It's very easy to actually get the products. The mechanism is what may confuse, but that's why we have spent more time on the mechanism. In the products at the long run, there's no big deal. The advantage of VTIC reaction over other method, it is more convenient than its rival, the Reformatsky reaction. The position of double bond is certain. In particular, it occurs with total position selectivity. The yield generally is greater than Reformatsky. It can take place in the presence of ester. Synthetic application of other things are also as provided. These are some of the class activity you can try on your own. If you have any challenge, you can ask later. In conclusion, we have been able to, 1, explain method of preparation of phosphorus halide. We have been able to discuss the mechanism and the stereochemistry of VTIC reaction. We have been able to describe the Honor-Wadsworth-Hemans reaction. We have given some synthetic application of Wittig reaction. We have also listed some advantages of Wittig reaction. So on this note, we have come to the end of this class for today. But I want us to have one more class, which must be this week. See you all by God's grace on Friday for the last facilitation that we have just fixed together. And that's going to be by 6 p.m. But before then, I'll still send messages to us all. Thank you, good night, and God bless you.